My name is Sonika. I'm a student of BSc Chemistry Honors second year. I'm going to read the chapter Chemistry of Elements of Second and Third Transition Series. In the previous chapter, we have discussed the position of transition elements in the periodic table. Transition elements belonging to D block of the periodic table and are located in between the S block and P block elements in the periodic table. The D block elements involve primarily the filling of the subshells. The penultimate shell in these element is being expanded from 8 to 18 electron by the addition of 10 electrons. We also attempted to define the transition element as elements which have partially filled D subshells either in the elementary form or their commonly occurring oxidation states. Strictly speaking, this definition excludes zinc, cadmium, mercury from the d block elements. This is because these elements do not have partially filled d subshells either in the elemental form or in their common oxidation state. The elements of group 12 do not show distinctly the properties of transition element except for the ability to form coordination complexes with ligands. However, for the sake of continuity and rational classification, the elements group 12 are included in the D block elements. In this chapter, we tend to explore the chemistry of heavier metals of D block, second and third transition series. The heavier metals of the D block are highlighted in figure 2.1. It is interesting to note that the 3D transition series, the atomic number of the elements of the second transition series are filled sequentially from 39 to 48. There is a discontinuity in the atomic number between lanthanum Z is equal to 57 and hafnium Z is equal to 72 in the third transition series. In brief, the second and third transition series that involve filling of 4d and 5d orbitals include the elements with atomic number. Second transition series ytterbium Z is equal to 39 to cadmium Z is equal to 48. 4d orbitals are gradually filled. Third transition series lanthanum Z is equal to 57, hafnium Z is equal to 72, to mercury Z is equal to 80. 5d orbitals are gradually filled. Electronic configuration of elements of second and third transition series. The general electronic configuration of the element of second and third transition series can be written as n-1 d 1 to 10 ns 1 to 2, where n-1 stand for the penultimate shell which occupy 1 to 10 electrons in the subshell, while n stand for the outermost shell that occupies 1 to 2 electrons in the s orbital. Table 2.1 lists the ground state electronic configuration of the elements of the second and third transition series. It is important to mention that the elements of group 7, 8, 9 are collectively called the platinum group metals. Now, general characteristic of second and third transition series. We have noticed clear periodic trends down each group in the chemistry of S and P block elements. However, transition elements of second and third transition series, the elements of periodic 5 and 6, show very strong similarity in their chemistry within the group but show large difference from elements of first transition series. This similarity is due to the filling of 4f orbitals in the element that lies between these two rows of elements. Period 5 and 6. Electrons in these orbitals shield very poorly the electrons in the outer 6s and 5d orbital. As a result of poor shielding, the effective nuclear charge increases with the result that the atomic and covalent and ionic radii of period 6 transition elements are reduced to almost same as those in the period. Let us discuss the important differences and the cause. First is the irregular or anomalous electronic configuration. In the first transition series, the 4s electrons are filled before the 3d electrons in the neutral gaseous atom. From scantium 2 onward, The 3D level continues to fill regularly with increasing Z, but at chromium, there appears to be an anomaly. In case of chromium, the electrons are so filled that 4s and 3D orbitals are each half filled. This is due to the extra stability which is associated with half-filled orbital. Similarly, at copper, the electronic configuration is anomalous because of extra stability which is associated with completely filled d orbitals. However, elements of second and third transition series display much more irregular electronic configuration in addition to half or completely filled d orbitals. The anomalous electronic configuration of these elements are attributed to the several electron repulsion. Second is the atomic and ionic radii. The atomic and ionic radii or elements of first transition series 3D are well known. However, the atomic and ionic radii of second and third transition series elements are not known with certainty, with the exception of few elements. As we move down a particular family of the transition metals in the periodic table, there is an increase in size from first to second transition series, but the size increase from second to third transition series is negligible. Oxidation state. The oxidation number of the transition metals are higher for the first half of each row than for the later member. Lower oxidation states are found to be more stable in case of first transition series compared to the elements of second and third transition series. The elements of second and third transition series have various higher common oxidation number than the first transition series. Like main group elements, the highest oxidation number of transition metal is found in case of oxide. The highest oxidation state +8 occur in case of osmium in OSO4. The other compound that exist in high oxidation state which have no counterparts in the first row are WCl6, ReF7, PtF6. It is also interesting to note that superficial similarities in the chemistry of second and third transition series element exist compared with the element of first transition series. For example, chromium, molybdenum, and tungsten all form the oxides with oxidation number +6. However, chromium oxide CrO3 is highly oxidizing, whereas molybdenum oxides and tungsten oxides are normal oxides of these metals. Reactivity. The elements of first transition C are more reactive than corresponding element of second and third transition series. The lanthanide contraction is majorly responsible for the low reactivity of second and third transition series. As an example, gold and platinum are least reactive. The low reactivity is due to the presence closeness of the valence electron to the nucleus. Because of poor screening of 4f electron. Because of poor screening of 4f electrons, the valence electrons are very tightly bound to the nucleus and are not readily available for chemical reaction. Now, fifth is the stability of the complexes. Transition metals have the ability to form complexes in contrast to S and P block elements. This is due to the small size, highly charged ions availability of vacant d orbital of low energy. In case of transition metals, the elements of first transition series form stable complexes with hard donors with nitrogen, oxygen, and fluorine, whereas the element of second and third transition series form stable complex with phosphorus and sulfur and heavy chalcogen donor. Coordination number. The coordination 6 is commonly found in transition elements, giving an octahedral structure. The coordination number 4 is less common compared to coordination number 6 is either square planar or tetrahedral structure. Complexes with coordination number higher than 6 are less common for the first transition series but are common among early members of the second and third transition series. Ligand-ligand repulsive interaction become more important with a higher coordination number, and thus it is the smaller ligand which allow highest coordination number. There are only few compounds in which the coordination number is 7. There are the three geometric forms known in this case and are shown as monocapped octahedral, pentagonal, bipyramidal, tetragonally capped trigonal prism. The capped octahedron is shown by tungsten complexes WBr3CO4 negative and NBOF6 3 negative. Capped octahedron is formed by the addition of seventh atom at the center of any one face of the octahedron. The pentagonal bipyramidal geometry is adopted by the anionic species zircon SZrF7 3 negative, UF7 3 negative, UO2F5 3 negative. Tetragonal capped trigonal prism is adopted by MF7 2 negative, where M is equal to niobium or tantalum. This arrangement is by putting a seventh atom above the center of one of the rectangular faces of trigonal prism. Coordination number greater than 7 are also known among the second and third row transition element. Coordination number 8 is found in the square entry prism as in Na3MoCN8 and dodecahedron in Bu4N whole thrice MoCN8. It is important to note that the solid structure is sometimes influenced by the counter ion, as in the case of Na3MoCN8, Bu4N3MoCN8. Coordination number 9 is the limit for covalently bound d-block metal complexes because this represents the full use of 9 valence orbital 1s3p5 d orbital. The anion ReH9 2 negative has tri-capped trigonal prismatic structure with coordination number 9. Seventh is aqueous chemistry. The elements of first transition series have a very rich aqueous chemistry. As an example, cobalt forms a variety of tetrahedral and octahedral complexes and display interesting aqueous chemistry. On the other hand, corresponding members of the second and third transition series, RH and iridium, they do not form complexes and do not have the aqueous chemistry. Most of the heavier metals, instead of forming simple cationic complexes, prefer to form anionic complexes in the form of halo complexes. The anionic complexes of heavier transition elements have rich aqueous chemistry. It is magnetic properties. Compound with no unpaired electron are diamagnetic, while those with one or more unpaired electrons are paramagnetic. Most of the transition metals compounds are paramagnetic. The diamagnetic arises from the circulation of electrons where induced by the presence of applied magnetic field. The circulation produces an induced magnetic moment which opposes the applied field and leads to the molecule being repelled by it. On the other hand, if unpaired electrons are present, applied field induces a magnetic moment which is aligned with the magnetic field. This effect causes the sample to be attracted into the magnetic field. Paramagnetism results from the interaction of spin and orbital angular momentum of the electrons with the applied magnetic field. If there is no interaction between the spin and orbital angular momentum, the magnetic moment spin plus angular of one atom or ion is related to the total spin quantum number s and total angular moment quantum number L by the expression mu s plus L under root g square s plus 1 plus L plus 1. The magnetic behavior of element of second and third transition metal ions is more complicated to explain as one has to take into consideration both the spin orbit coupling and the effect of covalent character in metal ligand bonding, where G represents the gyro-magnetic ratio. For a free electron, its value is 2.00023 or practically 2. Therefore, the above equation reduces to mu s plus L is equal to under root 4s s plus 1 plus L plus 1. The unit of magnetic moment is Bohr magnetron. In cases where the orbital angular momentum contributed reaction is quenched so that 4s plus 1 is greater than L plus 1, hence the expression becomes under root 4s plus 1. This is in fact the fact that spin only value of magnetic moment. This provides a good approximation of the observed magnetic moment mu for first row transition metal complex, and it is generally found to mu s is less than mu s plus L. In the case of high spin d ions such as manganese and iron, L is equal to 0, so that in case mu observed is equal to mu s. Thus, from a knowledge of whether the complex is high or low spin, the number of unpaired electrons in a complex can be easily calculated and its magnetic values is evaluated. Ninth is metal bonding. Metal bonding. Metal bonding is very rare in first transition series except in metal carbonyl such as Mn2CO10, Fe2CO9, Fe3CO12, and CO4 and CO12, and in carboxylate complex such as chromium acetate, Cr2CH3COO4, H2O2, and in solid nickel digloxime, NiDMC2. On the other hand, metal-metal bonding is very common amongst the heavier transition metals of second and third transition series. For example, they form carbonyl with metal-metal bond similar to those of first transition series Ru3CO12, OS3CO12, RH4CO12, IR4CO12. In addition, it forms RH6CO16. The heavier metals such as molybdenum, ruthenium, rhenium form binuclear carboxylate complex such as MO2CH3COO4, H2O2. The halide ion of this type Re2Cl82 negative and MO2Cl9 3 negative possess metal-metal bond. A unique feature of set of 5 elements of second and third transition series is that these form cluster in which there is extensive metal-metal bonding. The complex cation NB6Cl12 2 positive, Te6Cl12 2 positive have unusual structure. Both the cationic species contain 6 metal atoms arranged in cluster at the corners of an octahedron with 12 bridging halogen atoms across the corner. In these clusters, there is an extensive metal-metal bonding. Unlike the lower halide of 3D series, the lower halides of molybdenum and tungsten, MoCl2 and WCl2, exist as in hexamers, that is MO6Cl12 and W6Cl12. These present interesting structure as M6X8 4 positive, where M is equal to molybdenum and tungsten, X is equal to chlorine. 6 metal atoms which are arranged in cluster at the corners of an octahedron with 8 halogen atoms located above each of the 8 faces of the octahedron and bonded to 3 metal atoms as shown in figure 2.2. Chemistry of ReCl3 is interesting as it exists as trimer Re3Cl9. It consists of a triangle with 3 Re atoms with 3 bridging halogen atoms across the 3 corners and 6 halogen atoms that bridge to the other Re3Cl9. Abundance. All the 10 first row transition elements are widely distributed throughout the Earth's crust and the ocean. Iron is the fourth after oxygen, silicon, and aluminium. Titanium is the ninth, while manganese is the 12th most abundant element by weight in Earth's crust. The remaining transition elements of second and third transition series are very scarce, and taken together, these 20 transition elements constitute only 0.025% of Earth's crust in comparison with 6.2% of all the 10 first row transition elements. Molybdenum is a unique element among the second and third transition series that plays a very important role in human body. Technetium DC does not occur in nature. Ionization energy. The first ionization energy of an atom is the minimum energy required to convert 1 mole of gaseous atom in its ground state, electronic state lowest energy into 1 mole of gaseous unipositive ion. M gases M positive plus electron. The amount of energy required in this process indicates how strongly the most loosely bound electron is attracted by the nuclear charge. It has been observed that the case with which an electron can be removed from a transition metal atom is intermediate between those of S and P block element. The first ionization energy and the successive second and third ionization energy of the transition elements are plotted in Figure 2.7. An inspection of the Figure 2.7 carefully reveals that the third ionization energy increased more rapidly than the first and second ionization energy. As a result, these transition metals are better indicated by their third ionization energy. The variation of third ionization energy of three set of transition element from scandium to zinc, yttrium to cadmium, and lanthanum to mercury shows that there is a general increase in the ionization energy with a discontinuity after group 7. This discontinuity in these values corresponds to ionization from a doubly occupied d orbital. Example: the electronic configuration of iodine Z is equal to 26 is 3d64s2. The third ionization energy from the atom of group 8 to 12 are from doubly occupied d orbital and are consequently lower because of the increasing repulsion between the paired electron in the same orbital to the subsequent elements. This discontinuity between manganese and iron in the first transition series and between technetium and ruthenium in the second transition series reflect additional energy which is required to break into half-filled of the subshell of manganese and technetium, which involves maximum loss of exchange energy. Similarly, in case of europium, the third ionization potential does increase in the third transition energy series, where 4f7 configuration is reached. Thereafter, it falls back and thus increases again on approaching configuration at YB2 positive. In brief, the ionization energy increase irregularly across the third transition series and is regular in third transition series. Y. ZrCl4 is the most stable chloride of zirconium, when for palladium it is PdCl2. An inspection of the third and higher ionization energy of d block element reveals that the ionization energy of these elements increase with the increase in atomic number of the element due to large effective nuclear charge. Thus, this causes third and higher ionization energy of palladium very high, which make it energetically favorable. In addition, towards the end of the transition series, the d orbitals become more core-like. As a result, these are less effective in stabilizing higher oxidation state through covalent contribution of bonding. Taken together, the factors make higher oxidation state less accessible to the right of d block. In addition, there is a great loss of exchange energy in creating PD4 positive from PD2 positive, then zirconium 4 positive from Zr2 positive. Comparative study of the element of second and third transition series. We have already discussed the general characteristic of the element of second and third transition series special reference to the element of first transition series in the preceding section. In this section, we will like to highlight the chemistry of elements in different group or second and third transition series. An attempt will be made to compare the chemistry of these elements with the element of first transition series. Zirconium and hafnium. Group 4 consists of element titanium, zirconium, hafnium. Some of the unique properties of these elements are summarized below. We have remarked that the atomic and ionic radii of the transition element in a particular series decrease with the increase in the atomic number. However, compared to S and P block element, decrease in the radii along a particular series is not regular and uniform. In case of group 4 element, both zirconium and hafnium has large ionic and atomic radii than titanium. However, an inspection of the table reveals that both atomic and ionic radii of zirconium and hafnium are identical. As a result, these elements have similar chemistry. This is primarily attributed to the effect known as lanthanide contraction. All the elements produced outside a noble gas D2S2 configuration. The significant difference of zirconium and hafnium from titanium is that, unlike titanium, zirconium and hafnium only forms a few compounds in oxidation state below 4. Most of the stable compounds are in oxidation state 4. Both zirconium and hafnium form the binary tetrahalides. The tetrahalides can be prepared by the standard method MO2 plus C plus Cl2, NCl4 plus CO2, NCl4 plus HX, M plus X2 MX4, X is equal to halogen. All the tetrahalides in the gaseous state are monomeric and tetrahedral, but in the solid state there is a octahedral coordination through halogen bridging. The tetrahalides are readily hydrolyzed. The extent of hydrolysis, however, decreases from titanium to zirconium. TiX4 compounds are hydrolyzed to TiO2, whereas ZrX4 and HFX4 hydrolyzed to give ZrOX2 and HFOX2. ZrCl4 is hydrolyzed vigorously by water at room temperature to give oxychloride, which is stable to further hydrolysis. ZrCl4 plus 9H2, ZrOCl2 dot 8H2 plus 2HCl. The complex ZrOCl2 dot 8H2, which crystallized form dilute HCl, has been shown by X-ray to contain the ion Zr4OH8 H216A positive. Each zirconium atom is surrounded by 8 oxygen atoms. 4 oxygen form coordinated 4 water, 4 oxygen form bridging OH group. The coordination number of each zirconium atom in this complex is 8. Like titanium 4 chloride, ZrCl4 and HFCl4 are known to act as good Lewis acid. Therefore, these react with neutral ligands to form the stable adduct of the composition MX4.2L, where L is equal to triphenylphosphine ether. Zircon and hafnium have a high charge in +4 oxidation state. There is no partially filled d subshell that might give stereochemical preferences and have relatively large size 0.74 and 0.75 angstrom. As a result, the tendency to assume higher coordination number increase with zirconium and hafnium. Example where the coordination number reaches 7 or 8 are known with oxygen and fluorine ligands. The structure of the anions ZrF7 3 negative and ZrF8 4 negative are shown below in figure 2.9 and 2.10. The species ZrF7 3 negative is basically a trigonal prism with extra ligand attached to one face. There are variety of other 8 coordinate complexes in case of zirconium. These 8 coordinated complexes are of the following: carboxylate ZrO2Cr4, acetyl acetonates, ZrAcAC4, oxalate Na4, Zr oxalate 4, nitrate ZrNO3 4. Oxidation state 3. The reduction of the tetrahalide by the respective metals at high temperature and pressure yields the trihalides, which are colored compound 3mx4 plus M 200 to 600 degrees Celsius mx3. The well-known compound in three oxidation state are ZrCl3, ZrBr3, ZrI3, HFCl3, HFBr3. Niobium and tantalum group 5. Group 5 consists of the element vanadium, niobium and tantalum. Some of the unique properties of these elements are summarized below. Niobium and tantalum occur generally together and are separated by fraction crystallization of their fluorocomplexes. The atomic and ionic radii of niobium and tantalum are almost similar but greater than 3D analog vanadium. Although both niobium and tantalum are metallic, the chemistry in the V oxidation state are more similar to those of typical known metal. As a result, they do not form cationic complexes characteristic of a metal. Instead, these form a variety of anionic complexes typically of known metals. The coordination number of niobium and tantalum in these anionic complexes are generally 7 and 8. The stable binary oxide of niobium and tantalum are pentaoxide M2O5. M is equal to Nb and Ta, which are dense white powder. These are obtained by the ignition of other niobium and tantalum compound in air. These are very stable oxides and extremely difficult to reduce. Halides and oxohalide, niobium and tantalum form all the halides in their high oxidation state. The pentafluorides are obtained by the reaction M2O5CCl4 300 degrees Celsius M2Cl10 HF MF54. A unique feature of niobium is that it forms stable pentaiodide Nb plus 5I2 300 400 degree 2NbI5. The pentafluorides are volatile white solids melting below 100 degrees Celsius, boiling near 230 degrees Celsius. They have a tetrameric structure that is characteristic for other pentafluoride with MF6 unit and one bridging fluoride between each pair of metal atoms. The pentachloride are yellow crystalline solids that are obtained by direct reaction of metal with chlorine. X-ray study reveals that NbCl5 is a dimer in the solid state with the two bridging chlorides giving with octahedral configuration around niobium atom. The halides are readily hydrolyzed to give oxahalides of the formula MOX3. M is equal to Nb, tantalum. The oxahalides are covalent but less volatile than the corresponding pentahalide. The structure of NbOCl3 is polymeric and shown in figure 2.13. The oxochloride contain planar trinuclear oxygen bridges between the niobium atoms. Thank you.